So we're in 11.6 and we're talking about surfaces in space. All right, let's start by talking about a sphere. So we have a center at some point x0, y0, z0, and radius equals r. So I think we talked very briefly about spheres before, but if we extend what we know about circles, what would be the equation of this sphere? X squared plus y squared plus z squared equals r squared. So that would be a sphere with center where? 0, 0, 0 at the origin. So if our center is at x0, y0, z0, some point we're shifting our sphere.
X minus x0, x0 squared plus y minus y0 squared.
Plus z, yes. Z minus z0 squared equals r squared. So this is our standard equation for a sphere with a center at x0, y0, z0. So just extending what we know about circles. So this is our first surface in space is a sphere, and this is our equation. So anytime we have an equation with this form, we're going to have a sphere. And we can extend what we know about circles to work to solve problems involving spheres. So let me just ask you a quick question. We're not going to go through the entire process, but I just want to talk about how we would go about this. So we want the equation of a sphere with 5, -2, 3, and 0 for -3 as endpoints of a diameter. So I just want to talk about how we would go about solving this problem. I don't want to go through the solution, but what would we do?
Find the midpoint of those 2 points.
Find the midpoint of those 2 points, and that would be the center of the sphere. And so extending what we know, we use this by extending what we know about circles. We found the equation of the sphere. So how would we find the midpoint of the segment between these points? Just extending what we know about midpoint. Average each coordinate. The x coordinates average the x coordinates average the y coordinates. So x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. So we're averaging the coordinates. So find the midpoint of the segment between these points to find the center of the sphere. That would give us our x0, y0, z0. And then what would we do? Distance formula, divide by 2. So we use a distance formula on these 2 points, divide by 2. The distance formula would give us the diameter, divide that by 2 to give us our radius, and then we'd have our radius to plug into our equation. So that's just a quick kind of thinking problem as to how we would approach something like that. So our first surface in space is a sphere. Should be pretty familiar. We're familiar with circles, so we kind of extend what we know about circles to spheres. Our second kind of surface in space are cylindrical surfaces. Um, so, just to backtrack just a touch, we've talked about two surfaces so far. Our plane is our first surface. So our plane is a linear surface. We have a linear equation in each variable. So a plane is a linear surface. We have our spherical surface that we just talked about. A cylindrical surface will have an equation that involves only two of the three variables x, y, and z. I must think.
Oh, yeah, the feeding chart looks beautiful.
Yeah, you like it?
Yeah, it looks good.
Okay.
I think Rocky's been in the same place all 3 times ago.
So we have an equation that involves only two of the three variables x, y, z, and the graph of the equation in a coordinate plane is called the generating curve. So we'll have some equation that has only two of the three variables, and we have a generating curve. And the surface is not necessarily a cylinder like we think of a cylinder. It's not necessarily like a round kind of tube. The generating curve of a circular cylinder is a circle, but we can have lots of different generating curves that generate different kinds of cylinders. So if we as an example, if we want to sketch z equals y squared. So our generating curve is going to be a parabola. And our parabola is going to be in the YZ plane. And one of the difficulties when we're talking about surfaces is we're so used to thinking in the plane that it's hard to kind of expand our vision of what we're doing. So if we were to sketch this, I'm going to draw my coordinate axes here. And we have y, z, and x. So in the xz plane, we have this nice parabola, like so, my generating curve. So that's z equals y squared. But x can take on any value. For this equation, x can take on any value. So no matter what value of x I have, I'm going to have this curve z equals y squared. I'm going to have this parabola. So I can extend this parabola along parallel to the x-axis. So along here, I'm going to have a cylinder like so. A parabola. And this extends in the negative x direction also. X can take on negative values. So what I end up with is kind of a parabolic trough. It looks like a trough that water would run through. So it extends infinitely along the x-axis because x can take on any value. So this would be a parabolic cylinder. So our generating curve is a parabola in the YZ plane, and x can take on any value. It would be a very high trough, yes. The water is flowing in from a wormhole on the positive z-axis. But then where would it flow to? I guess it would never fill up. Right? All right. What's that? You'll never get above almost zero because it just, yeah. Yeah, if you had to paint the outside, you'd be in trouble. All right. Let's look at another example just to help us visualize these a little bit. Z, we want to sketch, and this is what I mean by we're going to be graphing, is we're sketching these graphs. It's not necessarily plotting points. So we're going to sketch z equals sine x. So our generating curve, in this case, is going to be a sine curve in the xz plane. So if we sketch a graph of this one's a little harder to sketch, and every year there's at least one student that when we sketch these three-dimensional graphs, does an amazing job. They'll sketch the surface and shade it and have the lighting coming from a certain direction, and mine's always wiggling and I have to erase stuff. So here are our coordinates. So in the xz plane, we have a sine curve. So let me try to sketch a decent sine curve in the xz plane. So there's our sine curve in the xz plane, and here is pi. And in this case, y can take on any value. So I can extend all along the y-axis. I'm going to have the same curve. So out here, I'm going to go out a little ways here. I'd have this same curve like so. And we'll say this is where it goes through the xy plane. And same thing a little further out here. Like so. So we're going to have this surface, and it's going to extend in the negative x direction also. So we'll have this surface like so. And I guess this little x should be here where it goes through the plane. And I have this kind of wavy surface. I think of this as looking like a corrugated roof. So it's going to extend infinitely in the positive negative x direction with my sine curve, and then the y direction is going to stretch out. So this would look like a corrugated sheet. Is the way I kind of visualize this one. Does that make sense? And we would call this a cylinder, because our equation involves only two of the three variables. So this would be a sinusoidal cylinder, I guess, is what we call it. Questions on that? To me, this is really fun. I really like visualizing this kind of stuff in 3D. All right, so we're going to talk about one other kind of surface today, and then on Thursday we'll talk about a couple of other kinds of surfaces. So our next kind of surface is a quadric surface. And these are the ones that start getting really interesting. The quadric surfaces. So this is our fourth basic surface. We have a plane, we have a sphere, we have a cylinder, and now we have our quadric surface. So our equation for a quadric surface is going to be a second degree equation involving the three variables in some way. So our x, y, and z, our equation is going to be a secondary equation, and depending on the form of the equation is what's going to determine what our surface looks like. The intersection of the surface with a plane is called the trace of the surface. And the trace of quadric surfaces are going to be conics. So we'll get to apply all the stuff that we know about hyperbolas and parabolas and what else? Spheres and ellipses when we deal with quadric surfaces. Now in your book on page 812 and 813, they have a nice table with quadric surfaces listed in their standard form with their traces. It can be helpful to look at those to have an idea of what we're talking about. I'm not a big one for memorizing formulas. A lot of people memorize these forms. Oh, it's this form, so that means it's this kind of surface. I kind of go about it a little different way. But that table can be helpful in visualizing some of these. But so it's good to be familiar with them. But I want to talk a little bit about how I would suggest you go about sketching graphs when we're dealing with quadric surfaces. All right, so let's look at an example. So we want to sketch and classify x minus y squared minus 4z squared equals 0. So I have a second degree equation. It involves all three of my variables in some fashion. So this is going to be a quadric surface. I'm going to rewrite this just to make it easier to work with. I'm going to write this as x equals y squared minus 4z squared. Sorry, plus, yes. So what I do when I'm looking at these, when I want to sketch this surface, is I look at the trace of the surface in the coordinate planes. So in the xy plane, we have z equals 0. So I usually think of it as covering these up. Is that up? We have x equals y squared. So what's that curve? That's a parabola, right? So we have a parabola in the xy plane. In the xz plane, when we have y equals 0, and we can think of covering up this term, I have x equals 4z squared. And what is this curve? Another parabola. So in the xy plane we have a parabola, in the xz plane we have a parabola, and parallel to the yz plane. So x equals a constant. If x equals some constant, what is my curve going to be? We have y squared plus 4z squared equals some constant. Almost. We have a 4 in front of the z and a 1 in front of the y. So that's going to be an ellipse. So for x equals some constant, we have an ellipse. So parallel to the yz plane, we have ellipses. So let's sketch this. This gives us our information we need to start sketching this. So here are our axes. This is y, x, and z. So in the xy plane, we have this parabola x equals y squared. So here's my parabola in the xy plane. In the xz plane, I have the parabola x equals 4z squared. So I'll try to do it in a different color and see if that helps. I'm going to have a parabola that comes in the xz plane up like so. And I'll put this one down below here. Like this.
Oh my goodness. Oh, I can see this.
And then parallel to the yz plane, we have ellipses. So if I connect these with green, if I connect these, I'm going to have an ellipse here. So what this surface is going to look like is, I think of it as kind of like maybe like a flashlight beam, I guess, but then the sides would be parallel, like the lens of a flashlight. So if you look at the lens of a flashlight, it's kind of parabolic, and it's kind of squished. So it'd be kind of a squished parabola on the sides, and it would just extend out this way. And the part that's facing us, the part that I kind of sketched here in green, these would be ellipses. So it's parabolic on the sides, kind of like a dome.
But like on the side.
Right. So it gets bigger and bigger and bigger, and it's kind of squished because we have an ellipse. Our ellipse is parallel to the yz plane. I'm trying to think of something that I have here. The best example I can think of is like the lens of a flashlight. If you look at the end of a flashlight where the bulb is, it's kind of it's parabolic, but it's the face of the flashlight is circular. This one would be kind of squished, so it'd be like a squished flashlight. Yeah, kind of going out like this. And to classify this, I would call this an elliptic paraboloid. So the elliptic comes from the ellipses that we have here parallel to the yz plane, and the paraboloid comes from the sides. So I would call this an elliptic paraboloid. So if we, and this is my suggestion on how you go about analyzing these, sketching these graphs, is look at the trace in the coordinate planes, and then try to, and then connect what the traces tell you to come up with your surface. In your book, In those examples, the last one that they talk about, the hyperbolic paraboloid, that one's probably the most difficult to visualize. But if you look at that example, it'll tell you what your traces are. I wanted to talk quickly about the hyperboloids. The hyperboloids take two forms. So and those are the second and third examples on the first page that I talked about. So a hyperboloid is going to have it can take two forms. I'm going to say x squared over a plus y squared over b minus z squared over c equals 1. So I have one minus sign here. So this is, when I have one minus sign, I get hyperboloid of one sheet. So one minus sign gives me one sheet. And if we look quickly, I just want to look at x squared plus y squared minus z squared equals 1, just to look at an example of this. So in our coordinate planes, in the xy plane, when z equals 0, we have x squared plus y squared equals 1, which is a circle. In the yz plane, I have y squared minus z squared equals 1, which is hyperbola. And in the xz plane, I have x squared minus z squared equals 1, which is another hyperbola. So if I were to sketch a very quick sketch of this, and we'll see, and then when we do the other one, we'll see why they call this one a hyperboloid of one sheet. So in the xy plane, I have a circle. So I'm going to sketch a circle here. In the yz plane, I have a hyperbola, and my hyperbola is going to look like this, and I'll sketch this one back here on the negative side also. And in the xz plane, I'm also going to have a hyperbola, and that hyperbola is going to go like so, right through here, and then go down here. And then same on the negative side also. And then if I go up parallel to the z-axis, if z is increasing, I get a circle. I get circles with larger and larger radii. So I'm going to get circles like so, going up and down. So I get this. The sides of this surface are hyperbolas, and if I tilted it on its side, I would get a circle that gets larger and larger and larger as I go along the z-axis. So with this one negative sign, I get a hyperboloid of one sheet. And that's because my surface is all connected. I just have one surface. If I have two negative signs, I just want to scroll this down. If I have something like x squared over a minus y squared over b minus z squared over c equals 1. This is a hyperboloid of two sheets. And the two negative signs tell me that I have two sheets. So let's sketch a quick graph of this one to see why we call it a hyperboloid of two sheets. And we'll do a very easy one. I'm just going to say x squared minus y squared minus z squared equals 1. So in the xy plane, I have x squared minus y squared equals 1, which is a hyperbola. In the xz plane, I have x squared minus z squared equals 1. So I have a hyperboloid, or a hyperbola in that plane. In the yz plane, I have minus y squared minus z squared equals 1. What does this tell me? When I square a number, I always get a positive. So I have I have a negative number here and a negative number here, and I'm adding them to positive 1. Can that ever happen? Adding two negatives to get a positive number? So this is impossible. So there's no trace in the YZ plane. So if I sketch a quick graph of this, and we'll see why we call it a hyperboloid of two sheets. There's z, y, and x. In the xy plane, I have a hyperbola, like so. And we have one back here on the negative as well. This is in the xz plane, sorry. This is the xz plane. So I have a hyperboloid like so, or a hyperbola, sorry. And in the xy plane, I have a hyperbola also. So my hyperbola goes like so. And same thing back here. And in the yz plane, I have no trace. And now if I look at this equation, if x is greater than 1, then I end up with circles parallel to the yz plane.
Is it like this on the positive and the other way on the negative? In the xy?
I'm sorry, is it?
Like you have one of them going down and the one in the negative side faces up.
So they face the opening, they're opening away from the z-axis. So this is opening away from the z-axis, opening away from the yz plane. Yes, so they'd be like
I get it.
two cups like
Yeah.
facing like this. And we would connect, so if x is greater than 1, I have circles. So my hyperboloid would have little circles connecting here, like so. So I'd have two kind of they look like satellite dishes facing away from each other. And they're disconnected, and there's no trace in the x or in the yz plane. So the circle comes from, if I look at the original equation, if x is greater than, if the absolute value of x is greater than 1, when I subtract that x from both sides, then I get a negative number on the right, and then I get y squared plus z squared equals some constant, and that's a circle. So if if the absolute value of x is greater than 1, I end up with circles parallel to the yz plane. So the main point of this is when I have two negative signs, I end up with a hyperboloid of two sheets. And we're not going to have a trace in one of the coordinate axes. But the best thing to do is to practice with some of these. So that's what we'll be doing. Homework. All right, there you go.
Is this on the page?